So, dear students, today we are going to discuss the very important equation that we come across in quantum chemistry called as Schrodinger wave equation. So, Schrodinger wave equation forms the heart of quantum mechanics. Okay, so from now onwards, when we are discussing any type of system, for example, if you are say for example we are studying to understand the structure of an atom, okay, then we are first applying the Schrodinger wave equation on a particular model. For example, if we are discussing the rigid rotator model of a diatomic molecule or a simple harmonic oscillator of a diatomic molecule to describe various spectroscopic events, again we are applying the Schrodinger wave equation on these models and trying to solve Schrodinger wave equation. So this Schrodinger wave equation forms the heart of quantum mechanics. So in order to discuss Schrodinger wave equation, we made some initial study on the concept of operators. Okay, this concept of operators will be very much handy to us when we deal with this Schrodinger wave equation. So before going to arrive at the Schrodinger wave equation, let us see some of the facts and features of Schrodinger wave equation and this new mechanics that is now called as quantum mechanics or wave mechanics. Okay, so in our previous series of classes, we have understood that the old classical mechanics or the Newtonian mechanics is not applicable for microscopic particle. It is only applicable for macroscopic particle. And why? What is the reason? The reason is an ordinary particle like a macroscopic particle, okay, only has particle nature, whereas its wave nature is very insignificant. On the other hand, the microscopic particle behaves both as a particle as well as wave, or in other words its wave nature is very much significant. So when we describe the behavior of a microscopic particle, we have to consider both of its particle nature as well as wave nature. But unfortunately the Newtonian mechanics only consider the particle nature. Therefore we have to develop a new mechanics which considers both particle nature as well as wave nature, and that new mechanics now we call it as quantum mechanics, or sometimes it is also called as wave mechanics. And the new mechanics, that is wave mechanics, that we have developed is consistent with the two important principles. That is, it is consistent with de Broglie hypothesis, okay, which considers the dual nature of matter such as electron, and Heisenberg uncertainty principle. The earlier Newtonian mechanics is not consistent with the de Broglie equation or de Broglie hypothesis and Heisenberg uncertainty principle, whereas the new mechanics that we are going to discuss or going to develop should be consistent with these two important principles, that is de Broglie's hypothesis and Heisenberg's uncertainty principle. So two different mathematical approaches were used for developing wave mechanics or quantum mechanics. One of the scientists was Schrodinger, who used a differential equation to develop wave mechanics, whereas the other person, that is Heisenberg, he used matrix method for formulating quantum mechanics. Since we are much familiar with the differential equation, and also it is easier to understand the physical meaning or significance of differential equation, we will concentrate on the Schrodinger method for formulation of quantum mechanics. So the Schrodinger wave equation, what is Schrodinger wave equation? It describes the motion of a particle. It may be a particle, may be an atomic particle or a subatomic particle, which has wave characteristic, okay, under the influence of a force exerted on it. For example, if you want to describe the motion of the electron, which is under the influence of the nuclear force, okay, so the nucleus at the center of the atom is exerting force on the electron, and due to this force, okay, due to the exertion of this force, the electron is behaving in some fixed manner. Okay, it may be revolving around the nucleus in a circular orbit or spherical shaped orbit, or it may be revolving around the nucleus in some fixed type of orbit. Okay, so how the electron is responding to the force. Okay, to describe that we have to use Schrodinger wave equation. We cannot use now Newtonian equations. We have to use this Schrodinger wave equation. And I already told you it is a differential equation. So Schrodinger wave equation is nothing but a partial differential equation. And the equation that we are going to discuss now is a time independent Schrodinger wave equation. So the Schrodinger wave equation does not depend on time. What does it mean? It means that only the position of the particle, say for example if we are discussing a three-dimensional system where x, y, z represents the position of the particle, so only the coordinate or the position of the particle x, y, z needs to be considered to describe the system. Or in other words, time is believed not to affect the description of the system. ಆ ಸಿಸ್ಟಮ್ ಅನ್ನು ಡಿಸ್ಕ್ರೈಬ್ ಮಾಡಬೇಕಾದ್ರೆ time is not a important variable. So since in chemistry most of the chemistry problems, okay, or events are independent of time, we always most of the time we use time independent Schrodinger wave equation. For example, the revolution of electron in a particular circular orbit, it only depends on the position of the electron and it does not depend on the time it spends in that orbit. So the structure of the atom could be understood by applying time independent Schrodinger wave equation. So when time will become important is, say for example we are considering a spectroscopic event where an electron from the ground state is excited to the higher energy state, which is unstable state. So the electron will rather spend a very small duration of time in the excited state and it will try to come back to its initial state. So the time spent in the excited state, okay, it will be a deciding factor explaining the behavior of the system. So in such case, in such spectroscopic events, the time is also a very important factor along with the position of the electron. So in such cases we have to consider a more general Schrodinger wave equation called as time dependent Schrodinger wave equation, which contains both time as well as position as variable. But we will stick on to the time independent Schrodinger wave equation where time is not a factor. Okay, and remember this Schrodinger wave equation cannot be derived, it can only set. We can only arrive at that equation by using some basic principles of physics. It cannot be derived, but still in a loose manner we call it as derivation of Schrodinger wave equation. Actually we are not deriving it, we are only just arriving that equation by using some basic principles of physics. So now let us go and try to set up or arrive at this Schrodinger wave equation. To be more specific, time independent Schrodinger wave equation. Okay, so let us now formulate a time independent three-dimensional Schrodinger wave equation. As I told you earlier, a Schrodinger wave equation describes the behavior of a matter which has both particle as well as wave characteristic. So a Schrodinger wave equation can be easily obtained by using two fundamental equations. One is called as classical wave equation, which represents a which mathematically represents a wave nature, and we have to use a de Broglie equation which gives a mathematical relation between particle nature and wave nature. So ನೆನಪಿಟ್ಕೊಳ್ಳಿ, Schrodinger wave equations obtain ಆಗಬೇಕಾದ್ರೆ two fundamental equation. One is called as classical wave equation, which is a mathematical representation of a wave, and the other we have to use is de Broglie equation, which gives a mathematical connection between wave nature and particle nature. So let us begin with the one-dimensional consideration, and slowly we will extend it to three dimension. So here I have shown a wave, okay, not periodic, okay, some kind of wave that is traveling along x-axis. So it is a one-dimensional motion. So this represents the origin, and the height of the wave from the equilibrium position, okay, is the displacement or the height of the wave is represented as u of x comma t. So the height of the wave, okay, or the amplitude of this wave depends on the position as well as time. Okay, so it is clear from the picture. So I have shown two incidences. the position of these two, okay, are different. Okay, so here x has some value x1, here the value of x is x2, and clearly we can see that the height of the wave at x1 and x2 are different. So the height of the wave, that is the value of u, depends on the position x. And also if I take one particular point x2, if I fix the position, and imagine this wave is passing through this point x2. So when this wave is moving through this point x2, what will happen to the height of this wave as it passes through x2? The height of the wave changes with respect to time. So the height of the wave, okay, is a function of two variable. It depends on position as well as it depends on the time. Now any wave, it may be an electromagnetic wave like light, it may be a sound wave, it may be a particle wave, and we are not discussing about these waves. Here we are discussing about a matter wave or a particle wave. What is that wave? It is a wave associated with a matter or a particle. So whichever wave it is, whether it is a light wave, whether it is a sound wave, whether it is a water wave, that is ripples, or whether it is the matter wave, any wave can be mathematically represented by a well-known equation called as classical wave equation. So any wave can be represented by a classical wave equation. Okay, this we are directly borrowing it from physics, that any wave can be represented mathematically by an equation called classical wave equation. And the one-dimensional classical wave equation is dou square u of x comma t divided by dou x square is equal to 1 by v square into dou square u of x comma t divided by dou t square. So this is the one-dimensional classical wave equation. It is a differential equation in terms of two variables x and t. That is why I have used this partial derivative. Remember, when do we use partial derivative? When we are working with more than one variable. So what is u of xt? U of xt represents the amplitude or the height of the wave at a particular value of x and particular time t. V represents the velocity of the wave. Since we are not discussing about an ordinary wave like light, we are discussing about a wave associated with the particle. So this V represents nothing but the velocity or the speed of the particle. So V represents the velocity. Okay, so double differentiation of the amplitude with respect to position is equal to 1 by v square, where v is the velocity, into double differentiation of the amplitude with respect to time. Okay, so this equation represents the wave nature of particle like electron. Now we have to solve this differential equation. There are numerous methods for solving a differential equation, out of which one of the most frequently used and most frequently used, and one of the more most easier, I think I can say it is one of the easier method for solving the differential equation is called as the method of separation of variable. Okay, so this is a well-known method. Okay, it is a well-known method. It is much easier to use and apply. Okay, that is called as the method of separation of variables, and this is one of the method that we will be using very frequently in our future classes when we will discuss about solving different types of Schrodinger wave equation. So as the name suggests, we are trying to separate the variables. What are the variables we have in this equation? We have variables x and t. So we are trying to separate the two variables from each other. That is, we are trying to separate x and t. So one of the important step that is involved, that is the first step involved in the method of separation of variable, is to write the overall function u of x comma t as product of two functions. The first function depends only on variable x, the second function only depends on variable t. Okay, so this is the first step of the method of separation of variable. We are trying to separate the two variables, and we have separated the two variables here because the overall uh, amplitude, that is the function, is written as product of two functions. The first function only depends on variable x and not on time. The second function depends only on variable t and not on uh, variable x. So we have factored out and separated the two variables. Now, as I already told you, we are formulating, or we are trying to obtain a time independent Schrodinger wave equation. So the equation that we are supposed to get does not contain time t. Okay, so we have to somehow eliminate this time, okay, which is not an important variable now, so it should only contain position x. So what we will do is we will set the function f of t. Okay, so if you see this wave is periodic in nature with respect to time, okay, but it is not periodic with respect to amplitude. If you consider a light wave, that light wave is periodic both with respect to time and position. But here I have selected a wave because we later come to know that a particle wave need not be periodic with respect to position. It may be periodic with respect to time, but it will not be periodic with respect to position. So since any wave of whether it is a light wave, a particle wave, it is always periodic in nature with respect to time, what we will do is we will set this function, okay, by an equation which represent a periodic function. So we will set here f of t as a into sine omega t. So this is an periodic function. This you have studied in your basic physics class, that a into sine omega t represents a periodic function. So this is nothing but a into sine 2 pi nu into t, where nu represents the frequency of the wave. So we are deliberately taking this expression for f of t because now we are assuming that the function with this wave is periodic in nature with respect to time. So let us substitute equation 3 in equation 2. We get u of x comma t is equal to psi of x into a sine 2 pi nu into t. So this is the expression for the amplitude u of xt, and this expression should satisfy equation 1. Okay, so we are trying to find out a solution for this equation, and we are assuming that this may be a possible solution. If this is a possible solution, what does it mean? This equation or expression should fit into equation 1. Then only it will be called as a solution for equation 1. So if you carefully look at equation 1, this function u appears as double differentiation with respect to x and double differentiation with respect to t. So what we will do is we will differentiate equation 4 twice with respect to x. Similarly, we will differentiate equation 4 twice with respect to t. What does it mean? We are calculating dou square u by dou x square, and we are also calculating dou square u by dou t square. Whatever expressions we get, we will substitute it into equation 1. So let us find out what is dou square u by dou x square. So let us differentiate equation 4 with respect to x, keeping time as constant. Okay, so we are taking partial derivative because there are two variables, and the rule of partial differentiation is you have to keep one as a constant and other as a variable. So now x is the variable, t is a constant. So let us take the differentiation in stepwise. Okay, first let us take the first derivative. So dou u by dou x is equal to, now when we are applying the rule of partial differentiation, remember now we are differentiating with respect to x. So when we are differentiating with respect to x, all the terms containing t should be treated as constant. Similarly, when we are differentiating with respect to t, all the variables containing x should be considered as constant. So let us first differentiate with respect to x. So this is considered as variable, these are constants. So let us take the constants. So it is a into sine 2 pi nu t. Okay, we are not differentiating it because it is treated as a constant, into differentiation d psi of x divided by dx. See here I have partial derivative dou u by dou x. Here I have ordinary derivative d psi of x by dx. Why? Because we are using partial derivative because there are two variables x and t. But here I am using an ordinary derivative because this function only depends on one variable x. Now let us again differentiate it with respect to x. You get dou square u x comma t divided by dou x square is equal to, again this is constant, a into sine 2 pi nu into t into, again I am differentiating, this becomes d square psi of x divided by dx square. Let us take it as equation 5. So equation 5 is the expression for the double differentiation of u with respect to x. So similarly, now let us differentiate equation 4 with respect to time. What will happen? Let us see. So now let us differentiate equation 4 with respect to time, keeping x as a constant. So we get dou u by dou t. Now we are differentiating with respect to t, so x term is treated as constant. So this is a constant, psi of x into, a is also a constant, differentiation of sine is cos of 2 pi nu into t, into differentiation of this term inside the bracket, it gives into 2 pi nu. Again let us differentiate with respect to time. So you get dou square u by dou t square is equal to, this is a constant, this is also a constant. Now differentiating cos, it is minus sine 2 pi nu into t into, here I have 2 pi nu term. When I am differentiating this cos term, again I have to differentiate the bracket, it will again give one more 2 pi nu into term. So it becomes 2 pi nu into 2 pi nu, that is 4 pi square nu square. Therefore dou square u of xt divided by dou t square is equal to minus a into 4 pi square nu square into psi of x into sine 2 pi nu into t. Let us take it as equation 6. So we have found or determined the double differentiation with respect to x and double differentiation with respect to time. Let us go back to our original equation, the wave equation, which is given by equation 1. The LHS of this equation is double differentiation with respect to x, which is nothing but here. RHS of this equation contain double differentiation of u with respect to t, which we have already determined. So now what we have to do is substitute equation 5 and equation 6 in equation 1 and see what will happen. An interesting thing will happen. Okay, interesting mathematically. Okay, what it is, let us see. So let us substitute. So on substituting equation 5 and equation 6 in equation 1. So in LHS, let us substitute equation 5. It is a into sine of 2 pi nu into t into d square psi of x divided by dx square is equal to 1 by v square into this term is given by equation 6 into minus a 4 pi square nu square into psi of x into sine 2 pi nu into t. Let us cancel out the common terms. A is common, gets cancelled. Sine 2 pi nu t also gets cancelled, and therefore we get d square psi of x divided by dx square is equal to minus 4 pi square nu square divided by v square into psi of x. Now if you carefully look at this equation 7, this equation 7 now does not contain the term t. So we have removed that term t, the variable t, from the wave equation. How did we do that? By setting f of t is equal to a sine 2 pi into nu t, by stating that the wave is periodic in nature with respect to time. So the wave equation is now independent of time and it only depends on position x of the particle, and this is a one-dimensional equation because it contains only one variable x. So equation 7 is a one-dimensional equation. It is not the Schrodinger wave equation, okay, it is the one-dimensional wave equation, okay, that is obtained by applying the method of separation of variable. Now what would be the corresponding three-dimensional equation, because our main aim is to find out the three-dimensional Schrodinger wave equation. So how will you write the three-dimensional equation? By, if you look at this equation 7, you can easily understand how to write the three-dimensional Schrodinger three-dimensional equation. In the LHS you have the term d square by dx square. So in 3 dimension you require two more terms, d square by dy square and d square by dz square. So LHS, instead of one this term, you should have total 3 terms. One is d square by dx square, that is with respect to x. The second term is d square by dy square with respect to y. The third term is d square by dz square with respect to z. And the other change that we have to make is this function psi of x contains only one parameter, that is one variable x. It is a one-dimensional function. Now we have to extend it to 3 dimension. So the psi of x should be replaced by psi of x comma y comma z. Okay, and you will simply call it as psi. So what is psi? Psi is nothing but equal to psi of x, y, z. So the corresponding three-dimensional equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. So instead of one term we have 3 terms, each term with respect to one variable x, y and z, and immediately you can see here a ordinary derivative is immediately replaced by partial derivative, because this function psi now does not depend on one variable x, it depends on 3 variables x, y, z, is equal to minus 4 pi square nu square divided by v square into psi. Okay, so this is the modified 3-dimensional wave equation. Still we have not used the other important equation, that is de Broglie equation. We have not brought into picture the particle nature of the matter. Okay, from equation 1 to equation 8 we have only dealt with the wave nature of the matter. Now we have to introduce the particle nature of the matter. How can we introduce the particle nature? What is the mathematical relation between the wave nature and the particle nature? That is provided by the de Broglie equation. Okay, so let us now use de Broglie equation and introduce into equation 8 the particle nature. So first let us define what is psi here. where psi is nothing but the function psi of x comma y comma z. Okay. Now we know that the velocity of a wave is product of its frequency and wavelength. This is a well-known equation that you have studied in physics, that the velocity of a wave is equal to frequency into wavelength, which can be rearranged as nu divided by v is equal to 1 over lambda. Nu over v, that is frequency divided by velocity, is equal to 1 by lambda, or nu square divided by v square. I'm just taking this square, is equal to 1 by lambda square. Okay, why I have took this step is, if you look at equation 8 here, I have nu square divided by v square. And what is nu square by v square? It is given by equation 9, that is 1 by lambda square. Okay, why I am doing this, you will come to know now. What we will first do is substitute. Okay, substitute equation 9 in equation 8. So we get dou square psi of x by dou x square, sorry, dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square is equal to minus 4 pi square. Nu square by v square is 1 by lambda square into psi. Why we have done is, we wanted to introduce this wavelength term in the equation. Okay, and the advantage of introducing this wavelength term is that now we can use the de Broglie equation. So what is de Broglie equation? According to de Broglie equation, wavelength of the wave associated with a particle is equal to Planck's constant divided by the mass of the particle into velocity of the particle. So a de Broglie equation gives a relation between wave nature of the particle and the particle nature. Okay, so lambda is equal to h divided by mv. So if we substitute this de Broglie equation in equation 10, what will happen? Let us see. So let us substitute this de Broglie equation in 10. You get dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square is equal to minus 4 pi square divided by, okay, h square into m square v square into psi. Okay, if I substitute in the denominator, lambda is equal to h by mv, I get this term. So if I take everything to LHS, it becomes dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 4 pi square m square v square divided by h square into psi is equal to 0. Okay, so we have to make some more changes in equation 11. What we will do is, we know that the total energy of a system is sum of kinetic energy plus potential energy. Okay, capital V represents the potential energy, not the velocity. Okay, don't get confused. Small v represents velocity, capital V represents potential energy. Therefore, half mv square is equal to E minus V, or mv square is equal to 2 into E minus V, or what I will do is multiply by mass m on both these sides. We get m square into v square is equal to 2m into e minus v. So we have obtained an expression for m square into v square is equal to 2m into e minus v. Why we have done this exercise, okay, is because here I have m square into v square. So what we will do is we will substitute equation 12 here for m square into v square. Then we get dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 4 pi square into m square v square is 2 into m into e minus v divided by h square into psi is equal to 0, which can be written as therefore dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 4 into 2 8 pi square m divided by h square into e minus b into psi is equal to 0. This equation, okay, this equation is nothing but one form of writing Schrodinger wave equation. So this is a very important equation in quantum mechanics called as Schrodinger wave equation. This is one way of writing Schrodinger wave equation. It is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equal to 0, where this function psi is called as wave function. It is a function representing the wave nature of the particle. That is why it is called as wave function, which here depends only on the position of the particle. Okay, x, y and z represents the Cartesian coordinate, that is the position. M is the mass of the particle. Small h is the Planck's constant. Capital E is the total energy, and capital V is the potential energy of the system. Okay, so this is one way of writing the Schrodinger wave equation. In the next class we will try to write the Schrodinger wave equation in different forms.